raise your hand if you are back. Awesome. Okay, so let's see what are the steps to solve a Newton's second law problem. So step number one is draw a picture with all forces drawn in. So you have to get them all. Okay, that's number one. Number two is we're going to write down net force equals ma for each mass in the system. Okay, so far we've only had one mass in our system. Blair, you had your hand up, but was that just on accident or question?
Yeah, that was an accident from earlier.
Okay. And Cody, same for you?
Yes, yes.
Okay. So in those problems, we only had one mass, but in later problems, we'll have more than one mass, and we have to write down net force equals ma for each mass. So then we split net force equals ma into x and y components. And once we've done that, we solve for unknowns. So the unknowns are often the accelerations of the different masses, but you know, it could be that in a particular problem we're given the acceleration and we solve for an unknown force, for example. Okay, so this is basically it. Now, number three, splitting it into components, there's a lot of the magic is sort of in doing that. Okay, that's the majority of the work, finding the components and getting the signs of the components correct. Once we get step number three done, what we will have is a system of equations. It could be one equation with one unknown, or two equations with two unknowns, or four equations with four unknowns, but it's always the same kind of thing. It's a system of equations, some number of equations with some number of unknowns. Now, often, once we have more than one equation with one unknown, that means just plugging in numbers doesn't help us solve because we have to do some algebra. So I'm going to encourage you to continue working with symbols and try to, I know you want to plug in numbers, but that is the crutch that will hold you back as things progress. It will hold you back not only from being able to perform on contests and solve problems, but it will hold you back from being able to understand the lectures. As we go, they're going to get more and more kind of, you know, intense. So you need to keep strengthening yourself and your ability to see and manipulate the symbols. And so this is a really good example. Solving for unknowns. When the problems are hard, we have a lot of symbols. You've got to be able to read that. So let's do another problem. Now, these are generic to every single problem, but then there are certain tricks that we will see we use in certain situations. Still more to the picture than this, but every problem will follow those steps. So let's try the following. Suppose I have a wedge. Okay, and on this wedge, I place a box. And frictionless wedge. We're still doing probably all today frictionless. So frictionless, and I want to know the acceleration of this block as it slides down this frictionless wedge. So first thing I have to do is I have to draw in forces. And I'll tell you what I think what I'm going to do is, I don't know if this will work or not, but let me try this. I'm going to share the blank whiteboard that you guys can draw on. So we have something like that. There's my block, and someone draw in a force. Let's see if you guys are confident enough to do that. Someone, you don't even have to tell me who it is, just draw a force. Okay, so go ahead. Okay, so we got the force of gravity. Now I like that, but what I'd like to do is have all of our forces, just pick like the center of the box, and all forces are going to come right out of that center. Okay, so someone else draw another force, maybe also in red. How many forces should we have? Anyone have an idea how many forces there should be? Awesome, we've got 2 more forces already. Any other forces that someone would like to draw? Just put your ideas up. You know, I can't even tell who's drawing them, so there's no worry about you got it right or you got it wrong. Okay, good. So let me switch to my whiteboard. I've got an idea what you guys are seeing there. We've got one that's down the ramp, one that's up the ramp, one that is straight up, and then one that is straight down. So okay, so here are the forces that I just saw. I saw a force like that, which we can call that the force of gravity. I saw an upward force, and I saw a force down the ramp, and I saw a force up the ramp. Okay, awesome. That worked exactly as I was hoping it would. So let's go through these one by one. Now, force of gravity, again, we should do that counting. You know, that counting where we count how many points of contact there are on the box. So how many points of contact are there on this box if I just let go of it? Anyone? Ziad?
3.
Where are the points of contact on the box?
So there should be the force of gravity, the other force that's showing it going down the wedge, and then the end force, the normal
Okay,
force.
now hold on. You're telling me, you're answering the question, how many forces are there, but I'm asking the question, how many points of contact? So I'm not ready yet to say what forces are there. I just want to know how many points of contact there are on the box. Okay, I'm going to put a poll up since you guys don't want to speak. I saw somebody. Okay. Answer this poll, please. How many points of contact are there on the box? Need a couple more responses. We're almost there. Okay. What I'm seeing in that poll, there are 1, 2, and snack. So we had 10 people who say 1 point of contact, 2 people, and 3 people who are having a snack. Now it's down to 2. Anyway, so most people are saying 1 point of contact. I agree. There's only 1 point of contact. This thing is just sitting on the ramp, and that's the only contact being made with it. So if there's 1 point of contact, there should be 2 forces only. Okay, and that's why this rule about points of contact is so important. Okay, we have 4 forces drawn in this picture. Okay, 4 forces. My whiteboard just stopped working. Okay, there we go. We have 4 forces drawn in the picture, but we should have only 2. And one of those should be gravity. So out of these 3 forces, they cannot all be correct. Even only one of them can be correct. So let's label them 1, 2, and 3. Now, force number 1. I'm going to try to get into, read your mind if you wrote down force number 1 or were thinking of force number 1, and think that that's friction, okay? And that if you're thinking about that force, you're absolutely right. If there is friction, which in our lives there really is friction virtually all the time, there should be force number 1. But because this is frictionless, we should not have force number 1. Okay, shouldn't have it. Force number 3. I'm going to guess that if you drew force number 3, you're thinking to yourself, there's something pushing down the ramp because it goes down the ramp. But if I ask you what force is creating 3, what point of contact is actually pushing it down the ramp, you can't answer that question because there is nobody pushing it down the ramp. It's not being pushed down the ramp. So that leaves us with force number 2. And I'm guessing if you drew force number 2, you're thinking about the normal force. And if you're thinking about the normal force, you're thinking correctly, sort of, to a point, but you're forgetting what the word normal means. The word normal means perpendicular, and so the normal force should look like this. Okay? Maybe I've got to move this thing a little bit because normal, oops. Well, I'll do that. The normal force probably is a little bit longer than that. Something like this. Okay, now let me pause because this is the correct diagram. There are only 2 forces. There's the force of gravity and there is the normal force, which is coming from contact. Now, remember normal's perpendicular. So the question is then, how is it, and I'm going to just maybe draw this force of gravity a little bit shorter so that the sizes match up with what I'm about to show you. But the object actually moves down the ramp. Okay, the object moves down the ramp. How can it be that it moves down the ramp when neither of the forces points down the ramp? Well, the answer is we just have to imagine moving the force of gravity and adding tail to head. So the net force vector just points right down the ramp. Okay? So it's not the case that either, you know, the normal force or the force of gravity is pushing it down the ramp, but the combination of those two forces winds up leaving, when we add the vectors, a net force that points down the ramp, and that's why this thing goes down the ramp. Okay, so let me undo that move so we can actually see what the picture should be looking like. Let me pause and see if you have any questions. Okay, well, then we have now drawn our picture and gotten the forces in. And, you know, that's the part of this that requires the most practice, is finding all the forces, making sure we know how many there are and which ones and which way they point, so that we can then proceed with the next points, the next steps. Haley.
I'm sorry, I do have a question now that I think
Okay.
about it. So whenever we're drawing in forces, should we always have the same number of forces as like points of contact?
+1.
You know what I mean? Like
Yeah,
plus
so
one,
you
okay.
+1 because of gravity. So however many points of contact +1, that's how many forces. That's exactly the point I'm trying to get across here. That's a really quick and easy rule for you to know if you've got all the forces. Okay, so this one had only 1 point of contact, so there should be exactly 2 forces. Now, the fine print is that friction and normal force together is 1 force. Okay, so if we had friction, we would have to lump the friction and normal force together and conceptually think of them as 1 force for the purposes of counting forces. But otherwise, that's exactly correct. So the next step for us is to write down Newton's second law. So we have net force equals ma, and this is a vector equation. We write this down for each mass, but in this case, we only have 1 mass, and we're going to just call that mass m. Then we split it into components: x direction, y direction. Now, there's an easy way and a hard way to solve this. Let me write down the hard way, but we're not going to do the hard way. I'm writing it down to convince you that you really want the easy way. And I know most of you already know you want the easy way. Okay, but just in case. So we would say net force, don't even write this down, okay? Don't even write this down. Net force in the x direction equals m times ax. And net force in the y direction equals m times ay. And if we look at the vector a up here, we can see, we can see clearly that it has an ax and an ay. Okay, so that's what we're referring to, the components of that acceleration vector. Now, in the x direction, we're going to have an nx up here. Here's n, and here's ny. Okay, so I'm kind of relabeling things. The hypotenuse is n. And then the opposite side of the triangle is nx, and the adjacent side is ny, if I'm thinking of this little angle there. So the force of gravity has no x component. So we're going to have nx equals m times ax. And then we come to the y equation. We're going to have ny and force of gravity y equals m times ay. Now, when I'm writing down my components, what I do is I list the components, but I do not put signs in yet. I put plus, 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 plus. I list them, and then if one of them is going to be a negative component, I put a minus sign in. So the ny, because it points up, is going to get a plus sign. But the force of gravity y is going to get a minus sign. Now, force of gravity y, in this case, is really the whole force of gravity. So I don't have to really put y on it. I just kind of understand that that is its own y component. Okay, now look at what do we have. If we assume we know the mass, which we don't actually know it, but assume we could measure the mass, so that's given, and that also means the force of gravity would be given. Let me do those in red. How many unknowns do we have? Well, we still have an x, and y, ax, and ay. So we have 4 unknowns left in this equation. Now, there's some kind of an angle inside of this normal force. So we could say that would be n times the, in this case, the sine of that angle. Now, I know that's unusual. Normally, x goes with cosine, but if we look at this right triangle, the opposite side is the x. So that would be m times ax. And over here, we have n times the cosine of theta minus mg, that's our expression for force of gravity, if you recall, equals m times ay. So given that this angle can be measured, and I will show you that it turns out that the angle of that triangle is the same as the angle of the ramp, that then leaves us with only, you know, just having trouble with my colors, n and ax and ay. So really, I only have 3 unknowns. And here, we have an angle theta as well, so I can call the ax, I can call that a cosine of theta, and over here, m times a sine of theta. And if I do all of that, I've got it down to 2 equations with 2 unknowns. But just, we don't want to do this. This is way too hard. That's way too much work, okay? Because there's an easy trick. Why is this so hard? It's so hard because the acceleration has x and y components, and the normal force has x and y components. And we wind up getting this sort of 4 unknowns, and we can reduce it to 2 unknowns, and it's very hard. But let me show you the easy way. Okay, so I'm just going to label this the hard way. I should give you extra credit for doing it the hard way. What's the easy way? The easy way is to just take our picture. Before I do that, I'm going to clean up this. Get rid of some stuff here. Okay. Now, the easy way is to just take our picture, and you can do this on your paper. I'm just going to move this thing out of the way for a minute. And we're going to take that, and we're going to adjust it so that the ramp is horizontal. Okay, so bear with me. I got to put my vectors back on it so we can see why this works. Okay, so I'm putting my vectors. I shouldn't have done these on 2 different layers. It would have been a lot easier to just rotate the whole picture. On your paper, the trick on your paper is just turn your paper at an angle. Now, I want the force of gravity to still point in the same direction it did, so I kind of have to rotate that, and almost there, move it. Okay, so that's what it should look like. It should have the acceleration just pointing exactly in the x direction. Let me clean that up a little bit. That would have been easier. That's what we called A, but now we could call it just AX because it's only in the x direction. And my normal force vector should, if I had done this correctly, should have been straight up and down. Okay, so what is the advantage of doing this? The advantage is I don't care about the y direction anymore. Okay, I don't care about the y direction because this thing only moves in the x direction. So in class, I call this the tilt your head trick. You just try to solve the problem with your head tilted at an angle so that the ramp no longer looks like it's a ramp. Okay, but you can also tilt your paper, or you can tilt your screen, or whatever. But the key is, this is a one-dimensional motion problem. It's motion in a straight line. It's just that we have this bias that we like to call horizontal, the x direction. If instead we call the x direction the one that points down our ramp, then we're in good shape. So how does it work once I've tilted everything? So in that case, when I'm looking at components, then the force of gravity has an x component and a y component. And the normal force only has a y component. So when I'm summing the forces in the x direction, I only have FGX component equals m times AX. And to get that component, there's an angle here, theta. And I'm going to prove to you in a minute that that is the same as the angle of our ramp. So that's going to be just the force of gravity magnitude times the sine of theta. Again, let me point out, like I did when I did the hard way, that we're used to the x going with the cosine, but in this particular case, it doesn't work that way because our angle is not the angle measured from the x-axis. So we have to be more careful. We have to notice that it is opposite to the angle, and the opposite side gets the sine. So we know force of gravity is m times g. And even though we don't know what the mass is, it turns out that it just cancels. And the acceleration, remember, the whole acceleration is just the x acceleration. The acceleration is just g times the sine of theta. So that if I just know what the angle of the ramp is, I can predict the acceleration. So for example, if this were a 30-degree angle, then we would have, if theta equals 30 degrees, I didn't really give a number, but we would have acceleration would be 9.8 meters per second squared times the sine of 30, which would be 4.9 meters per second squared. Remember, the symbol g is a positive number. Okay, when we did free fall, we said AY equals negative g, but the g itself is a positive 9.8. That's the same here. Anything that has a minus sign, the minus sign comes out when we write down our original equations and we put components in as positive or negative. If the angle is 0, that is, if our ramp is actually already horizontal, the acceleration we would get would be 0. It just won't accelerate. So go back to the original picture. If this angle is 0, meaning our ramp really is just a tabletop, the acceleration will be 0. If the angle is 90 degrees, which basically means you take your table and you start raising one side until the tabletop is actually vertical, then the acceleration will be 9.8. It just means the object will be in free fall. And any angle between 0 and 90, the acceleration kind of goes from 0 up to 9.8. All right. Any questions about the easy way? Because anytime we're doing a problem and we see a ramp, we want to do the easy way, not the hard way. Ziad.
So for the labels you have for the triangle under the block, what are those labels? I can't really see them.
In red?
Yeah.
They are, let me make them better. So we have F, G, Y, and F, G, X.
All right, thank you.
Sure. Okay, other questions? Okay, let me briefly show you how I know these angles are the same. So remember, the normal force is perpendicular to the ramp, and that means also so is FGY. Those are both perpendicular, so we're getting a right angle right here. Okay, I can also imagine if I took the force of gravity, which remember on the original picture is perfectly vertical, and it's going to be perpendicular to the ground. So there are two triangles we can look at. So there's this green triangle where we have theta, and this angle up here would be 90 minus theta. And then whatever, so if theta is 30 degrees, this would be 60 degrees, but these two, this theta inside my gravity triangle and this 90 minus theta, they make a right angle. So the only way that happens is if this theta is the same as that theta. Okay? So again, to put numbers, it makes it a little easier to think about. If this is 30 degrees for my ramp, then there must be a 60-degree angle here, and if this is 60, this must be 30. So same goes if this is 20, this would have to be 70, and then this little angle would have to be 20. And in general, whatever this angle of the ramp is, when we make gravity into a triangle, it's going to be the same angle at the top of that triangle. So that is something that you don't want to try to prove that every time you do it. You just kind of want to remember it. And you will be getting practice with inclined planes like this, where we have a plane that has an incline. And just every time we do that, make sure you remember that the angle of the ramp is the same as the angle in the gravity triangle. Okay, so this is what I would call the easy way. All right, any questions about the easy way or the hard way? Okay, so hopefully that will give you enough of an idea how to try some of the homework. If you see problems and you feel like you don't feel ready for those problems when you try the homework, that's okay. That probably indicates we need a few more examples. So kind of put a pin in those problems and do the ones that that you think are sufficiently similar to what we have done today, and and for the other problems, just kind of wait or ask me questions if you feel like you just need a little help. All right, that's it for today's lecture. I will stick around for a few minutes in case anyone has particular questions about your contest or how to make lab corrections or the lecture or anything. Otherwise, see you guys tomorrow.